I'm very happy to introduce Hal Daume today. He's an assistant professor at the School of Computer Science at the University of Utah. And before that, he did his PhD at USC ISI with Daniel Marcoux. And before that, I think he was at CMU, where he did math and logic and stuff like that. And he doesn't wear shoes. Even in this weather, he got here in sandals. So Hal is a member of the small club that seriously knows both machine learning and natural language processing. And he's always interesting to talk to. He's been doing a lot of non-parametric Bayesian methods lately. If you are interested in machine learning and getting good intuitions about machine learning, I suggest that you pay attention to his blog at nlpers.blogspot.net. .com, sorry, yeah. Apparently, when you have a blog, you sometimes get a fan club, and Chris Callison-Birch tipped me off that some people were wearing T-shirts at the MT Marathon in Prague. So there was this one. Did you not know about this?
I didn't know.
Apparently,
about
this. These images were on T-shirts. Oh, hang on. We've got to, let's see if we shrink this up here, that might work. Okay, there we go. Evidently, he doesn't need much more introduction since his minions around the world are already promoting his message.
Yes.
I'll just say that he's not only in the club of people who knows about machine learning and NLP, but also in the club of people who write very clear and worthwhile papers. And so I commend his webpage to you where you can download them. So let's get on to the talk, because it's not me you want to hear from.
Okay, so thanks, Jason. That was really nice. So I'm actually pleased because the last talk I gave somewhere else, they introduced me, and of course they mentioned my blog, which somehow I can't get introduced without people talking about. But it was also mentioned that I think it was described as, and Hal is probably most famous for his blog. And then I got a little bit depressed because I don't like to think that that's what I'm most famous for. It's maybe true, but I still don't like to think that. So anyway, all my contact information is there. Yeah, so thanks for inviting me. And if at any point during the talk you have questions, just go ahead and ask. I'd rather keep it kind of informal. So this is where I'm from. So you guys are keeping me from skiing today, which of course makes me a little bit angry. But I just wanted to put that up as a nice background. So these are sort of the people that I work with. This is basically the group of people who do NLP and machine learning stuff. So the guys in blue are the guys who have something to say about what I'm talking about today. So a lot of this work wouldn't be possible with them, or it wouldn't be possible without them. So they deserve credit. And I tried to be consistent and put little acknowledgments in the lower right corner if there's like a paper or someone's work that I'm talking about. And then this is also some of this stuff, specifically the machine translation stuff, is with Dragos Munteanu, who was an academic sibling of mine. He graduated, I think, like 6 months later under Daniel also, who's at Language Weaver now. I want to give a couple examples of what domain adaptation is all about. And so these are sentences from 5 different domains. And the point is just to convince you that like this phenomenon of domain does actually exist. So, okay, the first one is please rise then for this minute's silence. So does anyone want to guess what this is from? Yeah, so this is parliamentary proceedings. It could be a bunch of other things, but you know, since there's machine translation in this talk, it's probably Parliament. Okay, what about the second one? Shakespeare? Not one that I've read, at least. Okay, so this is obviously some medical domain. Okay, so what about this third one? Okay, so it's subtitles from some movie. All right, what about this fourth one? It could be Parliament. This is actually news. The fifth one, somehow, no one is ever able to guess. So I forgot to mention in yesterday's post that I also trimmed an overgrown huge hedge that spans the entire length of the front of my house and is about 3 feet across. It is not my blog. It's my mother-in-law. So When I told my wife, so this was from an IM conversation, this is not an isolated incident. She's like the worst IMer ever. So my wife is a little bit peeved that she's now getting like, every time I give a talk about domain adaptation, I have to use this example because I think it's just so great. Anyway, my wife isn't happy about that, but she should tell her mother to write more coherent IMs. Okay, so that's sort of what text can look like across different domains. So what might we want to do with text? I don't know how many people here are like NLP people, but we might want to do part of speech tagging. So we get this sequence of words, and we want to assign to each word the part of speech that it plays. So George Bush is a proper noun, spoke is a verb, and so on. We might want to do some sort of shallow parsing. So George Bush forms a noun phrase. Spoke is at least the head of a verb phrase. To is the head of a prepositional phrase. Congress and yesterday are each noun phrases. We might want to do named entity recognition, so we might want to figure out that George Bush is a person, Congress is an organization, or we might want to do machine translation and map this thing to French, and I'm not going to even try to speak the French because I can't. So these are basically the tasks that I'm going to be talking about today. So here's a little example of what goes wrong. So here we have a French source sentence, a reference translation. So this is how a human translated it. And this is in the news domain. So the human translation was both principles lie at the crossroads of philosophy, politics, economics, sociology, and law. And then we took an MT system that was trained just on parliament proceedings and had it translate this. So blue is basically what it gets right. Green is sort of like what it gets right, but not exactly as in the reference, and then black, it's kind of screwing up. So we get these two, so that's kind of like both principles to hold the philosophy, politics, economics, the sociology, and law. So maybe you can figure out what's going on here. If you do some sort of like clever adaptation, or not even particularly clever adaptation, you can essentially get a totally correct translation, even though it doesn't match exactly. So if you look at another example, you see something like Yeltsin had not afraid of nothing and did not consider its own survival, but to the survival of the democratic idea he was introduced in Russia. So somehow this is giving the idea that Yeltsin was being introduced in Russia when it was actually Yeltsin's idea that was being introduced in Russia, or rather the democratic idea that was introduced in Russia. So again, if we can do some sort of adaptation, we can turn this into a translation that actually looks quite reasonable. I mean, the first one's kind of hard to read.
Sorry, that adapted output is real output.
It's real output, yeah. Okay. So if you don't like qualitative results, I can give you some quantitative results too. So here we have 4 tasks, part of speech tagging, shallow parsing, named entity recognition, and translation. These are scores according to some metric, both in domain, sorry, this is both, this is on out of domain data, and this is just a model trained just on source data, and then this is if we've adapted the model. So part of speech tagging, we can go up from like 88 to 96, shallow parsing from 84 to 96, named entity from 96 to 98, translation from 24 to 28. So these are the different measures and the actual domains that we were using. So in particular, so the translation example is news or parliament to news, which we were using as a test case initially, but then we found out news actually isn't that representative. If you use medical domain instead of news, you get this jump from 19 to about 44. So this is a much, much bigger difference than the news case. All right, so I hope to have convinced you at this point that different domains exist and you should do something about it because otherwise your outputs aren't going to be very good. So if I haven't convinced you of that, you can like doze off or something. Okay, and so the other thing that I'm going to make clear up front is that the approaches that I'm going to be talking about all assume that we have a small amount of data in the target domain. So there's sort of another style of domain adaptation work where the assumption is I have, say, training data in parliament proceedings, and then I have a lot of unlabeled data in, say, the medical domain. That's not the setting I'm working with. The setting I'm working with is that I have a small amount of labeled data in the medical domain. So if you want the other, you should talk to like John Blitzer or Mark or someone like that. So, okay, so I call this the supervised domain adaptation problem.
And there's no unlabeled data that you're using?
No unlabeled data. Okay, so the first question that we want to look at is, well, what's going wrong when we try to move from some domain to some other domain, right? So we've seen sort of experimentally that performance drops, but what's actually causing this drop? So we tried to look into this, and I should confess that we actually looked into this after we had spent about 4 years doing domain adaptation work, which is probably not the right order to actually have done this in. But I'll present it in the order that we should have done it. So pretend we haven't done any domain adaptation work, so we're looking at what's going wrong. And so we tried to break things down basically into 4 possible components that could give rise to error when you move to a new domain. And then we mangled the words so that they all start with S, so that we can say it's like the S to the 4 model. Okay, so the first is seen. So you could screw up. I'm going to use translation as a running example because it's easiest to think about. So you could screw up translating the phrase diabetes mellitus because you've never seen the phrase diabetes mellitus in news or in parliament proceedings. So this is sort of like an out of vocabulary and unseen word issue. The second one is sense. So this is basically, I've seen this phrase before, but I've never seen it translated in the right way. So an example here would be if I go from news to technical documentation. In news, the word monitor is pretty much always a verb, meaning to like keep track of something. In technical documentation, monitor is almost always a physical object that sits on top of your desktop, right? So you might have seen the word monitor before, but you've never actually seen the correct translation. So then the third one is score. So maybe you've seen the word before and you've seen the correct translation, but when you were translating, your model just was stupid and it decided not to use this translation. It preferred some other translation because maybe it had a higher language model score, it had a higher translation model score, or something like that. But it was there, it just didn't get used. And then the final one is search. So you could have search errors that are cropping up when you're in a new domain that weren't cropping up in your original domain. We're kind of going to assume that this isn't an issue. So our assumption is that search errors cause as much of a problem in both domains. This may or may not be true, but measuring search errors is such a pain that we didn't want to get into doing that. So I'm pretty much just going to be talking about these 3. So seen, which is like OOV, sense, which is like sense, and score, which is like score. So okay. So that's our sort of like ontology of what can go wrong when you move to a new domain. So let's look at our component tasks for a second. So these charts take a second to read, but I'll try to explain what's going on. So we look at all errors made by a part of speech tagger. And we try to attribute the error to one of these 3 components. And so in the case of part of speech, we have labeled data. We can do this automatically. And so this inner circle here is the errors made when you run your part of speech tagger on in-domain data. So what we see is roughly like 85% of the error is due to out of vocabulary, which is basically common wisdom in part of speech tagging. Basically, all of the mistakes you're making in domain are out of vocabulary errors. Basically, none of it is due to word sense, so you've pretty much always seen this word used in this way before. And then there's some fraction that's used on score. So then when you move to the out of domain, we now move to like the outer piece of this strange pie. And what we see is that the out of vocabulary, the percentage of the error attributed to out of vocabulary is now significantly smaller. And sense really crops up as the biggest source of error. So what this seems to be saying is that when you're moving out of a domain, at least in part of speech tagging, the thing that's a big problem isn't out of vocabulary words, but just words that you've seen before but never seen used in this way. Okay, so that's part of speech tagging. Does it hold up? Oh, yeah.
So if you try to retag your training data, the purple stuff, of course, won't be there because everything will be seen. Mm-hmm. Do the sense versus score still break down the same way roughly? Do you have a sense? Did you look?
I don't know, actually. That would be interesting.
Because that would point to a weakness of the model, if you will.
Yeah.
Okay.
Yeah, I'm not sure. I should try that.
Yeah.
Are you in a situation where these 3 types of error actually interact? So that if you see an unknown word, it might trigger some sense that is wrong?
For a different word in the sentence? Yeah, so it could happen, and we would put all of the blame on the thing that actually was wrong, not on the thing that caused it to be wrong, if that makes sense. Okay.
So does this mean machine learning is not that useful? Because the only thing you can correct is scorecard, right?
Maybe. We'll see. Hold on a second. You're too clever. You jumped ahead too much. Okay, so this is part of speech tagging. All right, part of speech tagging isn't that interesting, so shallow parsing. Basically, the same thing happens. So we have this big out-of-vocabulary problem when we're in the source domain. The out-of-vocabulary shrinks dramatically, and everything becomes a sense problem. And actually, the score problem becomes even smaller.
If you had a fourth band here showing all the tags on which there was no error, I assume the out-of-vocabulary problem would actually grow. It's only shrinking as a fraction.
It's only shrinking as a fraction of the actual error, right? So yeah, the thing that's being hidden here is, of course, this is like 5% error rate, and this is like 20% error rate. So, but as far as a percentage of the error, it grows. Ah, that's a good idea. See, I'm not like a visualization person. I basically found this like cake chart in like OpenOffice, and I was like, oh, this looks really pretty, so I'll use this. Anyway, I think it gives a reasonable intuition. So, okay, so then if you move to named entity, so named entity isn't quite as clear. So named entity OV isn't actually a big problem. I think this is because like if it's OV, it's probably a name, and then you're pretty much only just trying to decide what type of name it is. Yeah. Okay, yeah. So capitalization, for instance, is a huge clue here that you lose if you go to like Chinese or something. Yeah, so I'm making no claim that this is going to hold up outside English. And here, I don't know. I mean, things actually stay pretty much the same. Sense becomes a slightly bigger issue, but it's not significant. So if we look at all of these together, I mean, I guess the big take-home message, and the thing that kind of surprised me is that, I'm used to thinking, or thinking in a sort of this domain adaptation sense that like unseen words are really going to be the problem. And it seems like that's not entirely true, or at least it's not the whole story. So I don't know. I found this kind of surprising. So the question is, as you alluded to, what can we fix here, right? So to some degree, it's going to be very hard to fix OOV. Although I guess like sort of the structural correspondence learning stuff that John Blitzer does can maybe do something of that. It's going to be kind of hard to fix sense. Kind of the place where we have the biggest room for improvement is fixing score, because this is basically the thing that the machine learning system has the most capability to affect. And so I guess our feeling based on these pictures is that we should expect not much improvement in shallow parsing, slightly more improvement in part of speech if we do adaptation, and then maybe a reasonably significant amount of improvement in named entity, which actually turns out to be kind of what we see. So it's a fairly consistent story. Okay, so we want to address this problem. So what can we do? So we can do one of four things, or maybe more things. So the first is the LDC solution, which is basically just pay some money and hire more people and have them annotate some data. And this is great because you usually get really good models if you do this. Unfortunately, it's expensive. I claim it wastes effort, and it's not really fun. So it's certainly not something I want to spend my time doing. The second is sort of the NLP solution, which is just pretend that domain adaptation isn't a problem and just train your parser or whatever on Wall Street Journal and just run it on whatever and kind of hope for the best. This doesn't work very well. So there's the ML Junkie solution, which is basically what I did back in like 2004. So I had like this long JAIR paper that talked about this complicated model for doing domain adaptation, and it took like 5 pages to derive like an EM algorithm. And actually, there were typos in the derivation, which I keep meaning to post like an errata to, but I haven't because I'm kind of lazy. And people cite the paper, but I don't think people even really care about the paper that much. So anyway, and it was also really hard to implement. There were a lot of like tweakable things. If you don't tweak them the right way, it doesn't work. It takes forever. It was fun to develop. I mean, I got to spend a week doing math. But okay, so fun is, I guess, in the eye of the beholder. But for me, it was fun to develop. And then there's this thing that I'll talk about today, which is this simple solution we had from this ACL 2007 paper, which works pretty well. It's really easy to implement. It's computational cheap. But I guess the biggest con is that there's no theoretical justification for why it should work, or in particular, why really bad things don't happen. So really bad things could happen, but they don't. And we'd sort of like to know why. So the reason that there's a but here is because I know of someone who has actually proved something about this model, but the paper was submitted to NIPS and got rejected from NIPS, and so I'm not going to be able to say anything about what the results are because A, it's not mine, and B, it's not published. So there's something you can say here, but beyond that, I'm not going to say anything more.
Who should we talk to if we want to?
I don't know if I should say that either. So maybe if you buy me a couple beers, I'll tell you who you should talk to. Okay, so hopefully, like maybe ICML this year or something like that, this will get out. It's an interesting result, and it actually corroborates a lot of the experimental evidence that I'll show. Okay, so here's our little example for part of speech tagging. So in news domain, so monitor is a verb and the is a determiner. In technical domain, monitor is a noun and the is a determiner. And so what we might want to do is, have some model that can say, well, there are certain things that are going to be common across the domain. So this is sort of the determiner-ness of the word the. And then there are going to be certain things that are going to be different across the two domains. And this is, this distinction between monitor being a verb and monitor being a noun. And so what we want to do is we want to take features of these words and we want to share some of the features, specifically the ones that have to do with the, and we want to not share the other features, and these are the ones that have to do with like the word like monitor. And I don't want to hand code which should be shared and which shouldn't be shared, so I just want some generic machine learning algorithm to figure out what it should do. So this leads to this feature augmentation approach. So here's the idea. So we have two sentences, one from news domain, one from technical domain. So we have we monitor the traffic, and the monitor is heavy. So what do? So we want to apply some machine learning algorithm like a CRF or something like that. So we're going to extract a bunch of features for each word. So for this word monitor, we might say that the word is monitor, the previous word is we, the next word is the, and the capitalization pattern is like a bunch of lowercase letters. And then here the word is the previous word is monitor, and so on. Then if we go over here, so now the word is the previous word is beginning of a sentence, it's capitalized, and so on. So, this would be some sort of generic feature set that you might extract. So what we're going to do is we're basically just going to make two copies of this feature set. And so since this example on the left came from the source domain, we're going to add features that say something like it's a source word and the word is monitor. It's a source word and the previous word was we. It's a source word and the next word is the, and so on. And then similarly on the target side, we're going to say it's a target word and the word is the. It's a target word and the previous word was beginning of sentence, and so on. So we've taken our feature space, we've triplicated each feature. I'm not really sure if that's a word, but we've made multiple copies of each feature. And then these generic features are shared across both the source and the target domain. These appear only on the source examples, and then these T1s appear only on the target examples. So if you don't like examples, if you like math better, so we take some feature vectors. So phi of x is the feature vector associated with example x. And we're just going to make our feature vectors 3 times longer. So in the source domain, we're going to take phi of x and map it to the vector phi of x. So this is the shared part. Phi of x, this is the source-only part, and then a vector of zeros of the length phi. And then in the target domain, we do the same thing, except we get a vector of zeros in the middle, and then phi at the end. Okay, so fairly straightforward. You can do this in MATLAB in like 1 line, or you can do it in Perl in like 3 lines or something. The interesting thing is if you think about, I don't know, I think this is kind of interesting. If you think about this in kernel domain, so if k is a kernel that corresponds to the features phi, then the dot product in kernel space between these augmented examples is going to be equal to the original kernel if they come from different domains, and it's going to be twice the original kernel if they come from the same domain. And so if you think about kernels as a measure of similarity, if you think about like an SVM is choosing examples that are supposed to help it classify, then basically what this is saying is I should trust training examples from my own domain twice as much as I should twice as much as I should, what was the verb I used? Trust examples from the target domain. I'm just making sure you're awake. Okay. So obviously now you look at it like this. Okay, there's this arbitrary 2 in here. You could make this some hyperparameter alpha, and you could try to tune alpha. But for the experiments I'll show, we didn't do that. We just left it at 2.
And just to be clear, the way you would end up tuning alpha is you'd multiply the latter values of 5 by something, right?
Yeah, something probably less than 1, but yeah. I should mention also, this is a totally redundant representation, right? I could easily get rid of this third column and just make this phi phi and then this phi 0, and you'll get exactly the same effect. So I just made it this way to make it easier to present. Okay, so we're going to compare this against a bunch of baselines. So I tried to use like every baseline I could possibly think of. So source only is we train only on the source data. Target only is we train only on the target data. All is we train on the union of the source data and the target data. Weighted is we train on the union, but we weight the target data differently. And this is now a hyperparameter, which we tune. Lin-int, so we train on source only, target only. We linearly interpolate the predictions made by both classifiers. And then there's this pred model. So the idea is I take my source only classifier, I use its predictions as additional features for something trained only on the target data, and then prior, I use the source only model as a prior for target only. So this is the like Chelba and Acero style model. So I've also distinguished these between whether they're instance-based or feature-based. So the ones that are instance-based, they're basically trying to do domain adaptation by playing with the examples as a whole, whereas the feature-based ones are trying to do domain adaptation by playing with features in the examples. And one of the things that I've seen, and I think other people have seen who do domain adaptation stuff, is that feature-based, at least for NLP problems, is kind of the way to go. It seems to work a lot better. So there's going to be a table that's going to be daunting, and it has like lots of sources, lots of tasks. We always do 75% train, 12.5% development and test. Evaluation is always Hamming loss and McNemar's test. So this is not totally great if you're doing like named entity recognition where you think F-score is better, but it holds up across F-score anyway. It's just easier to do statistical significance here. Okay, so here's the scary table. I don't actually expect you to like try to digest all these numbers. But here we have a bunch of tasks. So this is ACE named entity recognition, Connell named entity recognition. This is PubMed. I don't even know what this is part of speech tagging for PubMed. This is capitalization for CNN. This is tree bank chunking. And this is tree bank chunking also. And so what we see is we see the results for the source-only model, the target-only model, and then for all of the baselines, I've collapsed this down just to the best baseline. So I ran all of the like 5 baselines, and then whichever one does best, I'm representing its value. And so the kind of interesting thing is that it's very inconsistent which baseline is best, right? So if you asked me, I have to use one of these baselines because I don't want to use your approach. So which baseline should I use? And I kind of have to scratch my head and say, I really don't know, because the one that wins is like very different across the different tasks. So this is a little bit annoying. Okay, so then this is the prior model, so like the Chelba and Acero, and then this is the feature augmentation approach. So the blue guys are now the guys where the feature augmentation approach wins. So it's basically everything except these cases. So these cases are where I take some subset of Brown, so Brown CN, whatever CN means, and I treat this as one domain, and then I treat the rest of the Penn tree bank as another domain. So the sort of interesting point of comparison is if I consider Brown just to be its own subdomain rather than breaking it down into the different subpieces of Brown, then augment actually wins. But if I treat each subsection of Brown as its own domain, then augment loses, which was a little bit surprising at first. So, okay, so the question is, why does this happen? Like, what's the difference between the blue guys and the black guys? Because I want to get the black guys off of the slide because they make me look bad. So you can look for things that are sort of indicative of whether you're blue or black. And the distinction seems to be whether the source-only model beats the target-only model or not. Okay, so what seems to be happening is that if the target-only model is winning over the source-only model, then augment does well. If the target-only model works worse than the source-only model, then augment doesn't work. So sort of intuitively what this means is in order for the target-only model to be doing better than the source-only model, it means that you either have a fair amount of labeled target data, or the target domain is so different from the source domain that even a tiny amount of labeled target data is going to do way better than the source-only model. Okay, so my feeling is if source-only is beating target-only, then this has to mean that there's really not that much of a distinction between the source domain and the target domain, and so why are you actually doing domain adaptation anyway? So my claim is that we can't actually get rid of these black guys because it doesn't make sense to be doing domain adaptation in this case. You can argue about that, but this seems to be, we have some more experiments that we've done since these. This seems to hold up across other experiments. And then the theoretical results that I alluded to also have a piece that seems to suggest that this is a reasonable explanation.
How would you be able to recognize you're in that case?
Without labeled target data? With labeled target data, sure. Without labeled target data, I have no idea. I wish I could, but I don't know how.
And you could hope for a rescue here from unlabeled target data, which are not using it.
You could hope for, but I don't know how to do it. This is, yeah, so we're always assuming we have a small amount of labeled target data.
So those brown chunks are really, the brown corpus chunks are really small amounts of data.
Yes, they're tiny, which is probably why target only is dying.
Yeah, but if you had a lot more of it, you might have had a different story.
Yeah, so if you, so my conjecture is that if you got enough of it so that this number was now lower than this number, then it would start being okay again.
Because I would say that that's probably pretty small.
Yeah, these are definitely very, very small. Okay, so I'm going to come back to this issue of like the brown corpus and like the different pieces of the brown corpus in a second. So this was all on these component tasks. So the question that we were looking at was how much does this extend to translation? And so the unfortunate thing about translation is it's a lot harder to measure things like when I'm making an error, is it due to OOV, or is it due to word sense, or is it due to scoring? And so we came up with this, I don't know, sort of framework for trying to tease apart these differences. And so basically what we're going to do is we're going to take a source-only model, and then we're going to take like the best adapted model that we can come up with, which in this case is going to be some sort of like mix of the source data and the target data. And then for each of these issues, so for scene, sense, and score, we're going to try to figure out how much of an impact it has, either by upgrading the source system to be more like the mix system, or downgrading the mix system to be more like the source system. And we're going to do this upgrade and downgrade in a different way depending on whether we're looking at scene, sense, or score. And then we'll look at which training step produced it and try to alleviate it. I should say that we have more concrete results at this examine part so far than on the alleviation step. But I don't know. Talk to me in a couple months and maybe we'll be able to say more. So we're going to look at a bunch of domains. So we looked at news, MEO, which is medical texts, movie subtitles, and PHP documentation. I'm not going to present the subtitles and PHP documentation results. They more or less mimic the medical text results. So just to save space on the slides, I'm going to keep them off. Apparently I kind of screwed up the appear-disappear order when I was tweaking my slides. All right. So before we talk about this, I just want to make some quick observations. So using a target language model helps, which is not surprising. So this is between a 10 and 63% improvement. All right, so who wants to guess what's between a 10 and 90% improvement? Okay, so it's tuning on target data. So if you have a little bit of labeled target data to do like minimum error rate training or something, this makes between a 10 and 90% difference. What about 4 to 150%?
Using test data for training.
I would hope that would make more than a 150% improvement. Okay, so this is if we re-weight the mixed data. So if we don't just naively take one copy of the source data and one copy of the target data, if we do some intelligent reweighting. Okay, so these things are very easy to do. And I should mention that we're looking right now at doing adapted language models, but I'm not going to talk about that. So look for stuff that Frank Wood is doing. Okay, so now we get to our experiments to try to tease apart the different sources of error. So these took a little bit of time to figure out how to do right, and if you think that I'm doing them wrong, I want to know. But it's kind of hard to construct these experiments. Okay, so what we're doing for the scene problem, so we're working only in phrase-based translation right now. You could presumably repeat these for like syntax-based translation, but we're just doing phrases. So for scene, we're taking our source-only model and we're adding to it, so we're adding to its phrase table any phrases from mix that contain words that don't occur in the source phrase model. Okay, so the idea is if this word doesn't occur in the source model, it must be OOV. So any phrase in the mix that has it must have come from something that I see in the target domain. So this is our add setup. Our remove setup, so this is downgrade mix. So we're going to sort of do the mirror thing where we take mix and remove phrases that have source words that don't occur in the source-only model. Okay, so these don't give you the exact same phrase tables, but they're pretty similar because the mixed phrase table is roughly a superset of the source-only phrase table, but it's not exactly. Okay, so that's for scene. For sense, we basically do the same thing, except so we take the source, we look for phrases in the mix that contain so if we're going French to English, it contains a French phrase that we have seen before, but an English phrase that we've never seen correspond to that French phrase. Okay, so this is basically trying to tease apart phrases that we've seen the French, but we've never seen the right way to translate it into English. And then remove is basically the analogous thing for removal. Okay, so then intersect, this is probably actually the most straightforward. So we take the two phrase tables, we intersect them, and then the only question is, do we keep the phrase scores from the source-only model, or do we keep the phrase scores from the mix model? So these end up with exactly the same set of phrases. The only difference is how they're scored. Okay, so there are various things you can nitpick about these, but I think overall they're kind of reasonable. Okay, so what happened? So I said I'm going to present results for news and EMEA. And the results actually differ significantly between whether you're going from Parliament to news or going Parliament to medical. Okay, so now we have another interactive portion. So for news, okay, those of you who I've talked to about this so far today, you're not allowed to say anything. But if you're going from Parliament to news, where might be the biggest source of error? Any guesses? I'll give you a hint. I was surprised.
Score.
Yeah, it's score. So unseen words and word sense really had very little difference. Basically, all of the error is coming from score. And so this is the case where we're intersecting the phrase tables and keeping the scores either from mix or source only. One thing that we saw that's kind of funny here is that if we intersect the phrase tables and keep the scores from source only, this actually outperforms the source only model, essentially because we're throwing away junk that it's just getting confused about. But if we're able to take the scores from the mixed system, we do like dramatically better, like 4 blue points, something like that. Okay, what about EMEA? Seen, sense. Anyone say score? So it's actually seen and sense roughly equally. So OOV starts to be a big problem here. word senses that you've never seen before start to be a big problem here. So score is still like sort of a reasonably impressive part of it, but not nearly as much. So what this sort of suggests is that if you're going from Parliament to news, doing something like the feature augmentation might be expected to do reasonably well, because that's essentially aimed at solving the score problem, and here the score problem is by far the dominant factor. But maybe you shouldn't expect it to help so much in the medical domain. So, depending on your perspective, this is either good news or bad news. I guess I actually had this all as slides. So it turns out that the naive way to add, to try to do augment in phrase-based model is you basically add a feature that says, am I the source domain or am I the target domain? And then let like minimum error rate training learn a weight on this feature. It turns out this doesn't help at all. So what we had to do in order to get this to help, at least on the news data, is we had to add 3 features, each of which is binary. The first one is, does this phrase only appear in the source domain? The second one is, does this phrase only appear in the target domain? And the third one is, does this phrase appear in both the source domain and target domain? And if you give it that much information, it's able to figure out enough to get about a 1.5 point improvement. You actually get a similar improvement, also about 1.5 in EMEA, but this is 1.5 out of about 4 versus 1.5 out of about like 20 or something. So you still get the same absolute improvement, but it's not helping that much. For EMEA, we really do need new phrase pairs. So basically, the setting that we're working in is that we have lots of parallel. Oh, Jason.
Sorry, I think at first I misinterpreted what you just said, but it suggests an idea, if I did misinterpret it. So you said all you tell it is whether the feature appeared in the...
Whether the phrase pair.
Whether the phrase pair appeared in the source domain, target domain, and so forth. But that's not augment, right?
It's not exactly augment, but so one way of interpreting augment is, so from sort of like an information theoretic perspective, all I should have to do is add to augment, or to do augment is add a single feature that says, is this source domain or is this target domain? The problem is that if you then feed this into a linear classifier, it's not going to be able to learn anything useful. And so one way of thinking about what we're doing is we're taking this one feature, am I source domain or am I target domain, and then I'm doing like a cross-product feature space between that one feature and then the original feature space. So, okay, it's not exactly augment, but in my head at least it has a similar flavor. So you could do exactly augment. My fear was that minimum error rate training really dies when you have lots of features, and so we didn't try actually doing the full augment thing.
Well, what I'm wondering is, so when you ask, does it appear in the source domain or the target domain, that's actually a threshold at 1, right?
I see what you're saying, yeah.
Right, and so you could actually try to take into account something about the feature count. I mean, my thinking about this is fuzzy, and I'm not sure there's a principled story behind it.
Yeah. But you sort of want to take into account like how confident am I about it in the source domain?
Regularizing the augment features differently.
Right. So yeah, I mean, if you go back to like the original augment story, I think that it totally makes sense to regularize them differently. I actually think the most sensible thing would be to say, you're only allowed to have a source or target non-zero weight if you have a general 0 weight, right? But unfortunately, this is now a non-convex regularizer, and I hate non-convex things. So, but yeah, you definitely could regularize them differently. And yeah, you could do a similar thing here. And it would probably help.
Another way to think about it, if you had just one feature, whether it's in or not in the source, would be to take, in the setting of the linear classifiers, to have the 2 augmentation version where you have phi and phi0.
Right.
And then in that setting, you would say that in the full augment, every component of phi in the second case has a separate weight. And in this case, you're saying those are tied together to be a single number.
Yeah.
And you tie them to be a single number, you're saying it doesn't help if you allow 3 numbers over there. It already gives you most of the win of having a million numbers with millions of number of features.
Yeah, I think that's very true. Yeah.
So for the augmented feature space, when you do training, do you just merge the together set and then change the weight?
Yes. We reweight them.
The data sets are
The data sets. So effectively we add multiple copies of target. Okay, so we have lots of parallel Europarl data. We have lots of non-parallel EMEA data. We actually have parallel EMEA data too, but we're going to pretend we only have non-parallel EMEA data. And we want to learn translations for OOV things or translations for new sense translations for words. So the way that we're going about this is sort of abstractly. We're thinking about some distribution P, which is a distribution over English words. Say these are just OOV English words. And some distribution Q, which is a distribution over German words. And then basically, I want to find some sort of dictionary matching between English words and German words that make P and Q as dependent as possible. So this is sort of the opposite of trying to distinguish if two distributions are independent. I'm trying to find a matching that explicitly makes them dependent. So it turns out if you do this in kernel land, this turns into maximizing something called the Hilbert-Schmidt information criterion. And there was a paper about this at NIPS this last year. So the idea is sort of hand-wavingly is here we have 20 OOV English words. Here we have 20 OOV German words. And this is the kernel matrix that we get. And what we're trying to do is we're trying to find a permutation of this matrix to make this matrix look as similar to this matrix as possible. And so a permutation would give you sort of a one-to-one matching. We don't actually want a one-to-one matching. We want some probabilistic matching. And so what this turns into is if we let pi be sort of our soft permutation, we end up trying to maximize something like the trace of k pi transpose L pi. So pi transpose L pi, so pi transpose is just rearranging the columns of L, and then pi is just rearranging the rows. So it's trying to make them look similar. So we use some sort of projected conjugate gradient to do this. So the results are a little bit early. I was hoping that they would be less early, but and then we learn the kernel based on the Europarl words. So we've run experiments up to about 100 unseen words. The accuracy is about 85%, which in our comparison seems to be better than the Hagigi et al. CCA-based approach from ACL last year. But sort of an even bigger question is, well, once we have these new dictionary entries, how should we actually go about integrating them into the MT system? And the problem here, which I can't speak to, but which Dragos tells me, is that he's spent the past year trying to get hand-built dictionaries to help MT performance, and he's having a really hard time doing it. So my hope is that when we're in this setting where we're in a new domain and we either have these words or we don't have these words, my hope is that anything will help. Like, anything is better than nothing. So I'm hoping that his difficulty in getting it to work in the same domain is not going to carry over. But we'll see. This is, I don't know, the tentative hope is to have something for EMNLP on this. Yeah.
So you're trying to map the new words, like in Germany, based on the mapping that you had in English?
So, okay, so the setting is we have, say, like a 10,000 word dictionary from Europarl that we already know the matching, right? And so from this we can learn, so for instance, if we characterize each of these words by a bunch of features, we could learn feature weights or something like that. So this is what I'm calling learning the kernel. And then we take, say, the top 100 OOV words in German, the top 100 OOV words in English, and then we try to figure out what corresponds to what. And obviously there's a possibility that there will be a word on the English side that has no correspondence on the German side, but then the hope is we'd get sort of a uniform distribution over the German words. So this would only help OOV, it wouldn't help sense. Okay, so yeah, so this is ongoing. Hopefully we'll have some results soon. So the last thing I want to mention is sort of this question of like, what is a domain anyway? And this gets back to this issue of like the Penn Tree Bank and Wall Street Journal and Brown and the different subsections of Brown. So this is data from Mark. This is Amazon reviews. So we have reviews of appliances, kitchen electronics, I think, electronics, music, books, and so on. So I mentioned Mark and then he runs. I guess so. So anyway, the question is, you know, here we have now 8 domains. I don't really know how they're related to each other, so I've drawn a hierarchy that's obtained just by doing some sort of standard hierarchical clustering based on like the documents themselves. But who's to say that this hierarchy obtained by looking at like the words in the documents is that actually a good hierarchy to represent how classification decisions for sentiment analysis should actually be made on this data? So basically what we want to do is we would like some hierarchical structure that tells us how domains are related in such a way that we can use this hierarchy as best as possible to make classification decisions. And so the setting that we're going to work with is we basically say there's a little classifier down at each of these leaves, and then the branches in the tree essentially provide a hierarchical model that give us a sequence of like Gaussian priors on these weights, or on the weights associated with these classifiers. Basically what we've tried to do is we would say, if we had a hierarchy, we could construct sort of this Bayesian version of the augment method, essentially by doing some like Gaussian message passing on the hierarchy. But no one actually gives us this hierarchy, so we're trying to simultaneously infer a hierarchy and infer classifiers at the leaves. And so then there's this additional question of what if at test time someone just gives me a new document that's in a domain I've never seen. So we can do this. We construct like an expectation maximization algorithm. We use this coalescent as a distribution over trees, and it kind of all magically works. So what you see, so now we're looking at 4 of the target tasks in Mark's data, and this red line is the target-only model. The blue line is if you pool all the data together. The black line is if you do the augment approach, which in this case actually is not working as well as I would have liked. But then this hierarchical modeling approach really seems to win. And I think the distinction between these results and the results that we saw before is in the results we saw before, we always only ever had 2 tasks. And somehow when we go, 2 domains. Somehow when we go from 2 domains to lots of domains, the augmentation approach stops working as well. And I think this is basically because you're blowing up the feature space dramatically and you don't have enough data in order to estimate these parameters reliably. And so using this hierarchical method to share the data intelligently across the different classifiers gives you a big boost. The x-axis is the number of examples in the target task. And one thing that's kind of interesting, I don't think I put a picture on, but the hierarchies that you induce by this look markedly different than this hierarchy that we had based on just clustering the data using a simple clustering algorithm. So there does seem to be something to simultaneously learning the tree structure and the classifiers.
So are you maximizing or integrating the tree structure?
So the tree structure is our parameter. Everything else is a latent variable. So we're maximizing the tree structure, marginalizing over everything else.
Okay. So you marginalize actually over all the feature weights as well?
Yeah. So we have to. So when you're doing. So we do this both in regression and classification. In regression, you can do this exactly because we use Gaussian regression, and everything's Gaussian, and you can do whatever you want. For logistic regression, we have to approximate it. Okay. All right, so that basically brings me to the end. So my sort of, oh yeah.
Just to follow up, would it be feasible to integrate out over the tree structure? I don't necessarily believe there's a single tree. I might be willing to, or at least, sorry, I guess what I should say is I'm not sure that the mode over, that it would be, the distribution would be strongly peaked at a tree.
Yeah, you're probably right. I mean, we could, so for this coalescent stuff, we have like particle filtering algorithms to get a distribution. If you're willing to, quote unquote, do integration by looking at a bunch of samples, then you could try this. Yeah. The main reason I didn't is because the maximize algorithm is like n squared log n, the SMC is like n cubed times number of particles, and the particles die off really rapidly, so you need a huge number of particles. And I don't know. So Delon-Guerreur has a result that gets that back down to n squared log n, but you still have times number of particles. So it's much less efficient. So we primarily did this for efficiency.
Thanks. So another answer you could have given is, well, Jason, you were right the first time. It's not really a tree, and the way that information is shared across domains is more complicated than that, based on meta features or something.
Yeah, that's possibly true. I mean, the tree is just sort of a useful approximation. I mean, I don't, these domains, I'm not even convinced that like the notion of domain is a discrete notion, right? I mean, things kind of like move back and forth, and it's very unclear when you're in one domain and when you're in another. So, yeah. So I think that the interesting, well, I'll get to the open questions in a second, but I think my take-home messages here are, for NLP problems, if you're doing domain adaptation, the magic really is in the features, not in the instances. So if you want some sort of gain, you should really be playing around with your features, not trying to weight your instances in different ways. There are people who disagree, but that's my claim at least. So for the component tasks, OOV is sort of surprisingly not as big a problem as other things. For MT, so we started out looking at news, and then we got really excited because score was the biggest thing, and score was something we knew how to fix. But then one of my friends up at Microsoft basically told me, you shouldn't be looking at news because news is like not that different from Parliament. And so we started looking at other things, and then the story changed dramatically. And so, if you want some off-the-shelf, cheap approach to work with, I heartily recommend Augment. So, we sort of have this ontology of how to talk about errors. So, one question is, what does this say about other tasks? There's sort of this theoretical justification for the augment approach question. And then specifically to translation, how can we use these translation dictionaries that we're learning? There are lots of ways of doing kernel learning. What's the best way to do it? And then honestly, I think the biggest question is, what is a domain? How many are there? How are they related? When you get new data from a new domain, how do you do something with it? I mean, in the hierarchical framework, it's nice because I can actually try to insert it somewhere in the tree, and this is a case where I actually can integrate over all possible places to insert it in the tree, and then try to make predictions there. If I have a more complicated structure, this is going to be harder. But I'm really open to suggestions, and thanks for coming.
So it'd be great to have some not only questions, but also discussion. Hal is actually around here tomorrow as well, but I emailed Desiree, and she says he's kind of booked up, but if you want to talk to him, there might be room at lunch, for example. And when I was introducing Hal, I forgot to mention that he also does programming languages, and in fact has a system called the hierarchical base compiler, which is a little language for specifying non-parametric Bayesian models.
Yeah. So I have a question for the argument approach. So basically, what you do, you have some feature file in the source side, you have some other feature file in the text side. Now you're trying to define a joint feature, right? So you define a joint feature with that part is file in the source, or this part is file in the text side or not, right? That's what you.
Yes.
So this reminds me something about like class file stacking. So if you produce some output by the first class file, then you also produce some output by the second class file, then you can the system actually look at the output of the first one and the second one. I mean, is there any relationship?
Yeah, so I mean, I guess the closest thing we tried to that is sort of the linear interpolation approach. So our third classifier that you're referencing is basically one that weights them equally regardless. I mean, I guess you could imagine doing something more complicated, but I haven't tried.
Yeah, but is there any relationship?
Oh, is there a relationship?
But stacking means so let's say you have one class file produce some output, then you have another class file also produce some output. Now you're trying to see, of course, first, let's say they have investments, right? Now for the second one, you're trying to choose an output that is the best. Now you're trying to define some feature to see whether this feature also failed in the output of the first class file or.
Yeah, so this is sort of like system combination style. Yeah, I'm not sure. I'd have to think about it some more.
Slide where you showed the kernels and the problem of matching the vocabularies. You say that you try to optimize the trace of the product and you put the pi as the permutation.
Yeah.
Again, could you please tell us how you do the maximization of the permutation?
So it's actually hard. So this is basically a quadratic program in pi, which sounds great, and the constraints on pi are convex. Actually, they're linear. The problem is we're trying to maximize this, not minimize it. So it's kind of going the wrong way, right? So it's like this is a bowl, and then I have these constraints, and I'm trying to find a maximum, which is going to be one of the vertices of the hyperplanes that defines the constraints. So it's this unfortunate case where we actually have a convex program, but we're trying to maximize rather than minimize.
So this is not this is not hard problem, right?
It is hard.
It is
so
hard.
yeah, it's NP complete.
Okay.
Or it's at least NP hard. I don't know if it's NP complete. Yeah, so basically what we do is we do the standard thing for dealing with non-convex. So we do a bunch of random initializations. From each random initialization, we do basically a conjugate gradient, but we do this projected conjugate gradient where we basically project it into the constraint space and then take steps there. So I'm not claiming that this is the best way to solve this, but we've played around with a bunch of other ways to try to optimize it, and this is the only approach that seems to scale. So the others, if we run it on like 50 words in each language, it takes like 4 hours or something. And so we want to run on 1,000 words. It's just not going to work. So, but even so, this is like an n to the fourth optimization where n is the number of words. It's hard to imagine doing much better because you have these two n-squared matrices, and at the end, you're sort of trying to compare the information in these two matrices, and it's hard to imagine that you would be able to do better than n to the fourth. But maybe you can. Yeah.
That this optimization is a convex problem, right? Or understand how the pi is actually just an integer, like it has to have all the integers like that.
So, okay, so we relax it so that pi is a doubly stochastic matrix. Yeah.
Or something like all one like everything has to be different. So that like
Well, so we enforce constraints that the rows sum to 1, the columns sum to 1, and they're all positive.
Thank you.
Thanks.